Okay, let's work on another problem. So today we're going to be working on number 33, search and rotated sorted array. And I'm going to admit, this one stumped me for a good long time. And ultimately I decided not to even record the initial bit because I was just lost on this, or at least I just wasn't very confident, right? So I worked on this off camera for 41 minutes and 42 seconds is what I have recorded down. I have a handful of notes on my tablet, and I'm gonna basically walk through my solution on camera first, and then we can get started coding afterwards. So let's just put my phone aside first, and let's talk about this. So the first thing I guess I noticed is that this, especially given its O of log n runtime expectation, is probably a nuanced application of binary search, right? Some sort of divide and conquer algorithm that makes it so we don't have to necessarily check one half of the array so long as it fulfills a certain set of conditions. So with that in mind, I thought, okay, and this is something that really helps me out in retrospect, is sort of just taking this and sort of breaking it down into all of the possible cases. And something like this is something that has come up before. For example, within, I think it was insert interval. It was also something that I should have done there. Sort of really break down the problem into all of its separate cases, right? So the first thing to wonder is this array pivoted around such that we do not need to care about it? And what I mean by that is that, for example, is this array in the normal order? And this we can define because we know that it is a sorted array. We know for sure that if the array is sorted, then for sure that the left item will be less than the right item. So that's sort of our criteria to see if our subarray is quote unquote normal. If so, we can take the standard approach of binary search. And what I mean by that is that in the case of this normal approach, we can just do binary search, basically. We can check the middle. If it's less, we go left. If it's greater, we go right. Our second case is that suppose that we are pivoted around a non-standard index such that we are not dealing with think about it a little bit more. We are dealing with the non-standard pivot index, right? So now we have two other things to consider if we check the middle. So the main thing is that we will still check the middle. And there are really, I think, two outcomes from this. So I'll call this 2A. If the middle is right on the quote-unquote seam of the pivot, and this will be defined as left is less than middle, which is our current number, which is greater than our right side. If our right side is less than our middle, then we are directly on the pivot, right? In this case, what we want to do is basically check to see which side of this subarray from the seam of the pivot are we going to explore. And one thing that I want to experiment with, and one thing that I think may work, is that we can check if the number is greater than the minimum of the right side or smaller than the maximum of the right side. So if it is greater than the minimum of the right side, then we can go to the greater than the minimum of the left side, then we can go to the left. If it is smaller than the maximum of the right side, then we go to the right. Because if the maximum of the right side exists and our value is smaller, then it probably exists on the right side of that pivot seam. If it is greater than the minimum, then it probably exists on the left side of that pivot seam. Could be wrong on this. There may be other conditions that we need to account for. But yeah, that's basically what I think. The second possible condition is if the middle is completely within one side or the other of the pivot. And what I mean by that is that if we have left less than middle less than right, essentially, for really any case, right? If we have the pivot all the way or towards the higher end, then it will be up to basically the greatest number. And if it's on the other side, then it'll start off lower. But in any case, left less than middle less than right. If this is the case, then we can perform binary search as usual. So if this is the case where we're just completely on one side of the pivot, it's very similar in sort of what we do with the case at the top here where our array is in sort of normal sorted order. Because if we know that that our middle is contained within this section, we can say, okay, if it's less, then it goes on the left side. If it's greater, then it goes on the right side. No big deal. Of this subarray, of course. And in this case, because we are doing all these evaluations, and these evaluations are just constant time, then we can achieve a log n runtime. And our space will be, that's a good question, and constant space. As far as I can recall, I don't think we're using any extra space. So that's basically what I thought of as like an approach. I don't know if the conditions for specifically 2A is strict enough, or if we'll encounter some other nuance. But for now, I think this is a good place to start, and then we can sort of go from there. So I'm going to create two functions. I'm going to create a binary search with the nums int array, a target int, a left side which is of int, and a right side which is also of int. And this will return int. We will also return or have a search function which will have a similar signature to our initial, but will also include a left and a right. Actually, I'm not sure if we need this binary search, because we can incorporate it in here, I think. We'll start with just this search, and if it gets a little bit messy, then we'll move it into its own space. So search nums target 0 target dot size. Pretty standard stuff, right? We can say our middle value is going to be equal to our right plus left divided by 2. So this is our middle value. And then we can say if left is less than right, as it should be, otherwise. So condition 1, condition 2. Then we can return our if, or we can do a when statement, right? When mid. Mid is equal to target, or nums at mid, right? Return mid. When nums at mid is greater than the target, then we return search at nums target. When our number currently is greater than our target, then we need to go left, right? So left and then right, or mid. And then otherwise, we can just say return search at nums target mid plus 1 right. Oh, and when, let's see. When left is greater than if left is no, but that condition won't hold. We'll just say if left is greater than right, return -1 for now. Really not sure if this needs to be updated. We'll see. Otherwise, we can check here, and we can say val min, or yeah, min left is equal to nums at 0. Val max right is equal to nums at right. And nums at left, nums at right. We should probably do the same thing here. So we know that the numbers on the left is greater than or equal to the numbers on the right in this case. We need to set up a sliding window of sorts, or not a sliding window, but just a window of sorts. If right minus left is greater than or equal to 2, I think, because 0, 1, 2, we need an array of size 3, so 2, yeah. Yeah. Then if and left minus 1 is greater than 0, and left, or greater than or equal to 0, that's fine, and right plus 1 is less than nums.size, then we can say val left val is equal to nums at left minus 1, val right val is equal to nums at right plus 1, and if left val is less than nums at mid, and, or we can say max left, it's min left, max right. Nums mid is greater than max right. Else if min left is less than nums mid, and nums mid is less than max right. So the pretty standard way to go. Although we can just say here that if nums at mid is equal to target, we can just return target here. So we don't need that. Okay. This is condition 2A, condition 2B. So you are less than you, and you are less than you, then you are less than you, and all that fun stuff. And then we can say when mid plus 1, right. Actually, I can just copy this whole thing and paste it here. Or at least I should be able to. And then, let's see. And then now I need to check if the min left. So this is 2A. I think. So then we know that it's on the seam. If min left is less than target, else if max right is greater than target, else return 0 or -1. So this is the case that if both min left and max right fail. And in that case, you just go to the left side and the mid. And in this case, you go to the right side. Mid plus 1. Right. So let me think about this some more. And I'll be back in just a little bit, just need to validate the equation and then stuff like that. Right, this problem is officially taking way too long of my time. So this is going to be the first medium problem that I'm going to be doing a solution lookup for. And yeah. Okay, so I took a look at the solution. This is something that came out of cracking the coding interview. For me, I personally prefer sort of written solutions more than sort of audio or video explanations, ironically enough. So it appears that the insight is something similar to what I was going towards here, but something that I didn't quite get. So I think this is still fine. What we needed to check was the left and the right side. That is correct. But in relation to our current midpoint. And that was what I was missing. And the idea is that we know that the midpoint exists as part of one of the halves. It's either the left half or the right half. And if it exists within the left half, or if the left half is the normal side, then we should search that side for our value. Likewise with the right side. So let's see if we can retool this solution to be something that's similar. So check the middle. There are two outcomes. Relation to the left and right sides. So 2a is that left is less than mid. 2b is mid is less than right. And in this case, recurse left half. In this case, recurse right half. So let's move this like so. We can still print line and say condition 2. And we can say if nums at left is less than nums at mid, else. So this is 2a, 2b for the conditions, and then we can say return search on our nums with our target on our left to our mid, and return our search, our nums, target on our mid plus 1 to our right. And let's see. Let's take a look at this again. So it's not quite as simple as this. Basically, we don't recurse on the left half, but rather we check to see if the number falls within the range of the normal half. Otherwise, check the other. So actually what we can do is say var left is left, var right is right. But in this case, we say, in this case the left side is normal, right? So right is mid, and in this case, the right side is normal, so left is mid. And then we can say that if actually we can just get rid of that entirely. We can just do something a little bit simpler. We can say if our target is greater than our nums.left and our target is less than our nums at mid, then return search on our nums with our target on our left and our mid, else return our search nums target mid plus 1 right. And likewise, if target is greater than our nums at mid and our target is less than our nums on our right, then return our search nums target mid plus 1 right. Otherwise, we do the same for our left side. So basically we are trying to find the normally sorted side, and we are comparing it. So if it exists within our normally sorted side, cool, then we recurse on there. If it does not exist within our normally sorted side, then we check the other side, because it wouldn't exist in our normal, because it doesn't exist. It just doesn't exist within our normally sorted side. Oh, looks like I missed the comma here. So that's the basic idea of this part. And let's see, do I even need to keep condition 1 there? That's a good question. I wonder if we can make this even shorter, more concise of a solution. Let me think. In a normal binary search sorted array that is not pivoted, then we know that is of one of the sides. Um, and in that case, it will do pretty much this search right here. It will do this search first, right? It will go through 2A first, because left is, of course, less than mid in a normal binary search. And in that case, then it will go through this. If it's greater than our left side and less than our mid, then it'll search there, and otherwise it'll search there. So I think we can actually get rid of condition 1 entirely here. And have this be our only case, right? Because the normal binary search falls within this condition right here. And we can say, or we don't necessarily need to know which direction it takes, because we have the logging of the indices already, so we can check that. This is fine to return -1 there. Let's just make sure that these brackets are as where they should be. This should move 1 up. This should not exist. This is just here to appease the compiler. Though really, I think we can actually get rid of it, because we have this exhaustive else case now. We'll see about it. Okay. So I think this is sort of the first draft of the solution that I'm fairly happy with. And then we can run it through, not a submit, but a run code, and let's see where we go wrong here. Okay, looks like we ran it into an out of bounds exception for the first one. We went with 0 and 8. This should be -1. Is there any other situation where that needs to happen? Nope. Cool. So it looks like it worked for these two. Let's toss through all the example cases, and let's see where we go wrong. Ooh, it looks like we're running into an infinite loop, yeah. Which one would that be? Looks like we run... Wonder if it's U. Let's try the first one. Between 4 and 7, and we're looking for 0, right? We know that 0 is less than 4 and 7, so it should exist within the right half, which is between U and U. So 0 and 7. 1, 2, 3, or 0, 1, 2, 3, 4, 5, 6. Yeah. So 0 and 7, our midpoint goes to this 7 right here. Then it's not within, of course, 4 through 7, so we check between 0 and 2. Let's see. 0 and 2. So 4 and 7, we did that. And then we get 0, 1, 2, 3, 4, 5. 5. And this should be less than. So we go 6 and... Or why do we go 6 and 6? Hmm. Number on the left is less than the mid, so we go here. Then target is not greater, so we go to less than or equals to, and I think this should also be less than or equals to. I think we hit an edge case there where it was exactly equal to one of the ends. And actually we might run into another edge case. I want to see if we can run into an edge case on one of the other ends, and it looks like we will. Let's take a look. So it's definitely not this one now. I'm guessing it's this first one, where we're at 3. Yeah, it looks like it. Let's see where we're going wrong. Should go to like, does it like break at like 6? Okay. 4 and 0, 7, yep. 4 and 7, yep. 6 and 7, yep. And then it just stops there. Wonder if that was screwing it up. Let's see. If target is greater than, so 3 is, so this is the 4 and 7 case. Right, because actually we're still in this case. So target is greater than left, but it's not less than the mid. So we recurse right, so that brings us to 6 and 7. Then 6 and 7, the midpoint would be 13 over 2, which would still be 6. So 0, 1, 2, 3, 4, 5, 6, so it's 2. And the target is greater than mid, but it's not less than u. Under what circumstance do you want to do that? Actually, no, it would still go back to this case. The target is greater than what's on the left, which is 2. But is not less than here. Why does right decrease? Let me think about this some more. Okay, there you go. This one was tricky. I think I had the right sort of initial starting point with binary search. to the credit of the problem itself, it also said for logn runtime, right? So it pretty much had to be binary search. I had a decent idea with the left and right ends, but I just didn't really make the connection that one side of the array, no matter what, would be, I guess, sorted up until the midpoint. I'm really not sure sort of what the lesson here is. Like, just sort of dig into, I guess, the input and then see what we can, like, see what sort of, I guess, facts we can establish. But this is a weird one. But in any case, I hope you learned something, and I'll see you for the next problem.